Right, but so when you think about scalable, you might be thinking about yourself adding on it. Now imagine that you're writing your own thing with these objects, and I'm writing my own thing with these objects, and now you and I have to communicate with each other. Now it could be a big org mess.
If right, that's
could be
what makes object-oriented programming so great. Is when you say, when you set something, this is what you're supposed to do. When you
well, kind of, but then I could have my code, you could have your code, that both touches the same object. And now you could be doing things to the object that I'm not anticipating, and I could be doing things to the object that you're not anticipating.
And you say functional programming.
That's not a thing. The only thing that's going to happen are exactly what you have there.
And that's another thing that I'm curious about in functional programming is oftentimes, like I said, you need to use the same class to do multiple different things, and you need to come at it multiple different directions. This API call wants to do this and this and this with it. This API call wants to do this and this and this, and they're all kind of coming in different ways, and then coming out different ways. And I cannot imagine that functional programming could produce that result. Like be useful.
You'd have to come at the architecture completely different. So much hard for us to reason about.
Yeah.
Yes.
Okay.
Anyways, before we jump into today's topic, Turing machines, got stuck on something last week that was annoying me, and I went back and thought about it and figured out what it was, and it was obvious. All right, back to the post-correspondence problem. So you remember we were saying that I was telling you that we could solve the post-correspondence problem if we could determine if a grammar was ambiguous. Mm-hmm. Okay, so here's how we do it. Because remember what we got stuck on was ensuring that if we generated a string with a grammar, we also generated a string with a grammar following the same rules, order of rules. Mm-hmm. You remember that was our problem? Mm-hmm. And so the fix is obviously include the order of the rules as part of the language generated by the grammar. So here's our post-correspondence problem. Here's A with roll 1 is a 1, B, roll 1 is 3 1s, roll 2, roll 3, you remember all that? Mm-hmm. Here's how we generate the grammars. Ignore that for a second. For A, the grammar we generate is, you can do a 1, we can still use A again, and then generate a 1 on this side, saying we used rule 1 first.
Okay, alright.
And then, right, 2 with a 2, that with a 3, or the empty string. Same with the B. Now when I combine both those grammars together with this, now this grammar being ambiguous is logically equivalent to solving the post-correspondence problem.
Right.
That make sense?
Yeah.
Yeah, I don't know why we couldn't think of that, but
because it's a review of what post-correspondence is about.
Oh, that's not something you're going to have to remember going forward.
Okay.
So, you can just watch last lecture, we just used that as an example problem, and then got stuck on something that was bugging me, because I knew it should have been easy. And got stuck. Okay, so, just wanted to point that out. And now we'll move on to Turing machines. Chapter 3, I think. Starting chapter 3, Turing machines. So up till now, we've been working with push-down automata, PDAs, right? Roughly speaking, a PDA has a state control. This is where we have all our states and all our arrows and how you transition. It had an input, where we talk about the string that we're actually reading, the one that we're determining, are we going to accept this string. And then it had access to a stack that I could read and write to. Right? Mm-hmm. A Turing machine now still has a state control, but now it only has a tape, so we don't have the stack anymore. The tape is infinitely long, not just big enough to fit our input. So the tape is infinitely long. And our head now can not only read from the tape, but it can also write to the tape. And the head, instead of up here, every time we write an input symbol, our head automatically moves to the next symbol. Our head automatically moves to the next symbol. So it only moves to the right. With a Turing machine, we're allowed to move our head to the left or to the right. Other major differences, PDAs were inherently non-deterministic. Our Turing machines are going to be deterministic. So for the input, there's one and only one thing that the Turing machine can do. Some other differences. A PDA only accepted if by the time we finished reading our input, we ended up in an accept state. A Turing machine, notice that's no longer a thing anymore. There's no such thing as we finish reading our input until we're done, because it might want to write some stuff and read some stuff again, and write more stuff and read more stuff. So a Turing machine has a special accept state, and once it goes into that accept state, it just accepts, period. So it's not a matter of ending up in that state to accept. If it ever goes in there, it accepts. Similarly with its reject state. If it ever goes into the reject state, it just rejects. Okay, so I think those are the major differences. Any questions so far?
Sounds a lot like just a normal computer at this point.
Well, that's what it is essentially supposed to be. A normal computer with random access memory. Yep. Okay, so if there's no questions so far, intuition for a Turing machine. What can it do? It can read and write to the tape rather than just reading from the tape. It can move the head to the left and to the right rather than just always moving one to the right. It has an infinite tape rather than just having the input on the tape. It has an infinite tape. And it immediately accepts or rejects when it enters those associated states. Good? Okay, so those are the big ones. So now, before we get to its precise definition, let's do an example where we actually draw out the diagram for one of these machines. Okay, so here's a language we're going to do. We're going to do a language that we've already done a bunch of times. This is not a language that we need a Turing machine for, but drawing these Turing machines can get kind of big, so it's a language that we've seen a bunch of times, and we're just going to use a Turing machine to recognize it. We could recognize this with the PDA like we already did. Okay, so here's the idea on how we're going to do this with our Turing machine. So our Turing machine, when we begin, our Turing machine always starts out with the input written on the tape, and then all the infinite boxes to the right after that just have what we call the blank symbol, etc.
Infinitely or the same?
Yeah, it's an infinite tape. So infinitely far to the right, can do this. Infinitely far to the right, it just has blank symbols from there on out. So here's an input that's in our language, 0 to the n, 1 to the n. Here's an example of an input that's in our language. What is our Turing machine going to do? Our Turing machine, we're going to have it go to the 0 and replace it with x, and then go to the right and 1. We can replace it with an x as well, but I'll try and follow what we do here because I tried to follow what the author said to do. He said replace 1 with a y. So we're going to start out with a 0. We're going to start like this. My Turing machine is going to start looking at this. I'm going to replace my 0 with an x. And I'm going to keep going to the right until I see a 1, and I'm going to replace it with a y. And I'm going to go back until I find my first 0 again, and I'm going to replace it with an x. And then scan to the right until I see a 1 and replace it with a y. I'm going to keep going back and forth. If by the time I finish marking off all my 0s, I finish marking off all my 1s, then we know that we're good. So let's start with some of our new notation for how we write these things. Make sure I don't accidentally do the wrong order on any of these. So first thing we're going to do is, here's our start state. First thing we're going to do is go back to our start, how we had it. 0, 0, 1, 1. What do I want to do when I'm right here and I see a 0? I want to replace it with an x and move to the right.
Okay.
So our notation for that is we write what we're reading, comma, what we're replacing it with, arrow, which way we move. I read a 0, replace it with an x, and move to the right.
I see.
Okay.
So you can do 3 things per, okay.
I can read something, write something, and specify which way I move.
What's the symbol for not moving?
There's no such thing as not moving.
Oh.
But you can move to the right, then move back to the left if you want.
I see. Interesting.
Okay, so now that replaces with an x, and now our head is right here looking at that 0, right? Now what do we want to do?
If it's a 0, you're gonna read a 0.
You want to
So if
think
you read
it
a
goes to
0,
the right,
print
basically.
nothing, like epsilon, I guess. I don't know.
Right. Okay, so you've got the right idea. You're saying if we read a 0, we just want to leave it as a 0 and move to the right.
Right.
Right. So the way we say that is, if we read a 0, we can write a 0, move to the right. That's one way we could have written it.
Mm-hmm.
When you do the same symbol twice like that, it's okay to just do this. 0, 0, and move to the right, and not specify a right. So that's understood to be read or write a 0, and move to the right.
How do you say that exactly again?
This?
Yeah, if we were to tell you that instruction, what would we say?
I would say if you read a 0, move to the right. Technically, it's if you read a 0, write a 0, move to the right.
Okay.
Which is the same as if you read a 0, move to the right.
If
Because you didn't change it.
move, okay.
If this, go that way. Okay. So that is going to take our head all the way here till we get to a 1, right?
Yeah.
Okay, now what do we want to do when we see a 1?
Read a 1, write a y, and move to the left.
Perfect. So if we see a 1, we write a y, and we're now going to move to the left. Make that arrow longer. And so we replace that with a y, and now we move to the left. Okay, now we're seeing a 0. Now what do we do?
Read and write a 0 and move to the left.
Right, keep going to the left. So let me make sure I put my arrows. I don't need to come back to this one, so we can put the arrow right there. So if we read a 0, we go to the left, right?
Yeah.
And that will take us back, all the way till our head's right here. Now what do we do?
Read an x, write an x, move to the right.
Right, and
Well, hold on. So we gotta move to the right and then write an X.
right, so once we're right here, let me just put it, you're saying the right thing. We're going to, if we read an X, we move to the right now.
Mm-hmm.
And that puts us right here, and now we're ready to restart the process. Right?
Okay, so you got write an X, move to the right. Okay.
Read an X and move to the right, so now we're right there. Now we take that 0, we replace it with an X, which moves us right here. Now we move right through all our zeros. Now we got to a Y. Uh-oh, what should we do in our Y?
Move to the right.
On a Y, we still want to move to the right. So we move to the right on all our zeros, and we also, for every Y, we're going to move to the right.
Yeah.
Until we get to a 1. When we see that 1, we're going to replace it with a Y. And move to the left, which puts us right here. So now we're in this state.
You need
When we read a Y, we should also move to the left again, right?
Yeah.
So when we see a Y, we move to the left, which gets us here. When we see a 0, we move to the left. And we keep doing that until we see an X. When we see an X, we move to the right, which gets us back here. And now we're going to repeat the process, obviously. So that will replace this with an X. We'll move over all the way until we get to here. Replace that with a Y. We'll come back to here, move to the 0, replace it with an X. And now let's follow this one through. So here we just replace our 0 with an X. So now we're right here looking at the Y. For the Y, we keep moving to the right until we get right here. Right?
Mm-hmm.
Well, hold on. I think you have to replace the one with the Y.
Well, we're still here. Now we're, oh, thank you. I didn't draw my head where I meant. Good catch. So we moved right through all our Y's in this state.
Uh-huh.
Now we replace one with a Y, which gets us to this state. That puts us here. Now we move left through all our Y's, which gets us to here. Now we read the X, which moves us to the right, which gets us right here. So here now, if we read a Y, what should we do?
If there's a Y, then we move.
Yeah, now we're going to go to not quite an accept state yet.
Yeah, is there a way to, do we have to like move to the end, or how does that work?
Maybe we could just go to an accept state. Let me see what I did here.
Oh, that wouldn't work because if our string had more 1s, then it would still go to that accept state.
Right, okay, yeah. So, because we could have potentially still had another 1 right here that we didn't know about.
Right.
Right. So here on a Y, we can go to the right, that's fine. So now we're right here. Here, we continue on a y going to the right until we see what?
If there's an empty.
Until we get a blank symbol.
Blank symbol.
Right. And then on the blank symbol, doesn't matter which way we move, right or left, we finally go to our accept state. Okay, so that was drawing out a Turing machine. Now, you'll notice that we didn't explicitly write the reject state on here. It's understood, since this is deterministic. Anytime we don't have the transition arrow there, you instantly go to the reject state and reject, and you're done.
Oh, so there's a single situation where there's no if something and they're all false and it's all rejected, or what?
Right, so if I start out right here, and my first input symbol was an X, notice that right here, reading an X, we don't know what to do.
Yes.
So we reject.
Okay. And that we just assumed?
And that's understood from this machine. If the transition isn't in this machine, then that means go to the reject state.
Okay.
Because we don't want to draw all the transitions that go to the reject state, because that's a ton of them.
Yeah, which is basically every other case.
Yeah, every other case from every state. So, be annoying to do that. So this is typically how people draw out Turing machines.
I don't think this machine accepts just 0, 1 because of that extra arrow. Read a Y, write a Y, go to the right. But I could be wrong.
Easy enough to think it through, right?
Yeah.
0, 1, blank, blank. So we start out here. 0, we replace it with an X and move to the right. 1, we replace it with a Y. Which gets us here.
Okay.
On a Y, we move to the left. So now our head's right there, right?
Mm-hmm.
Here, on an X, we move to the right.
Oh, okay, I see now.
On a Y, we move to the right. On an empty symbol, doesn't matter, we accept.
Right, okay.
So, I think we're good. Here it is, you know that? Okay, so that's an example of drawing out a Turing machine. And you'll notice that this was a lot more tedious than our push-down automata version of this thing.
Mm-hmm.
That's the way Turing machines are. And so we'll see a few more examples of Turing machines, but then we'll see how people actually write out Turing machines when they have to. Hardly anyone ever goes to this detail anymore, because for even simple Turing machines, it gets very tedious. But notice that once you understood how to do the procedure up here, you were kind of able to figure out all this yourself. So typically what happens when people give you a Turing machine, what they really do is they give you a description of the process to do up here. And then they assume that with that description, if you sat down and thought about it long enough, you could come up with a Turing machine if you needed to.
Okay.
So we'll see examples of all that. Anyways, okay. Now what exactly is the definition of a Turing machine? Let's go over its exact definition now. A Turing machine now is a 7-tuple, Q, sigma, gamma, delta, Q not, Q accept, Q reject, where Q is a finite set of states, sigma is the input alphabet, where the blank symbol is not allowed to be in the input alphabet. In this example, what was our input alphabet?
Is it
What was
0?
sigma up here? Sigma up here was just 0 and 1. The letters that show up in the language we're recognizing.
Oh, okay.
That was our input alphabet. You're not allowed to have the empty symbol in your input alphabet, otherwise you'd be trying to read an infinite string as your input. Right out the door. Okay, so sigma here is your input alphabet. Gamma here is your tape alphabet, where you have to have the empty symbol in your tape alphabet. The tape alphabet is anything you can write on your tape. And sigma, your input alphabet, always has to be a subset of your tape alphabet. You have to always be able to write your input string on the tape. So up here, our tape alphabet was that we had 0, 1 in there. We also had the blank symbol. We also had X, and we also had Y. Those were all the symbols we wrote on the tape. Okay? Delta, your transition function now, it takes a state and a tape symbol, and it spits out the new state to go to, the new tape symbol to write, and whether we move the head to the right or the left. So going from here to here, if this was state Q0 and this was state Q1, our input was Q0 and 0, and our output was Q1, X, and R. Reading this transition function. Delta makes sense? And then Q0, in Q is the start state, Q accept in Q is the accept state, and Q reject in Q is a reject state. Pretty straightforward?
Yeah. Can there be multiple reject states though?
No,
But there can be 0?
but it's easy enough to make there's one and only one reject state, one and only one accept state. And one and only one start state. And
Right.
allowing multiple accept states doesn't change anything, because you can just make all those states go to your one accept state.
Right, but in our example we didn't have any reject states, so it's okay for there to be 0?
We did have a reject state. It's implied in your diagram. We don't actually draw it out.
Oh, okay.
It's implied that all the transitions that we didn't put here go to the reject state.
Okay.
And it would just be, make the diagram unreadable
Right.
and actually write it. Yeah.
Okay.
Okay, good. Any other questions on that definition? Cool. Alright, now we have a notion of the configuration of a machine. Let me give you a concrete example of the configuration of the machine before we read that, and then I think it will make perfect sense. So, in order to do that, we need to name our states. Q0, Q1, Q2, Q3, and then Q accept. Right? Reading some input. So the input we were reading was 0, 0, 1, 1, 1, 1, and then blank symbols, right? Now somewhere along the way, we were at the point where we were X, X, Y, Y, and reading this symbol, 0, and we were in the state Q1, moving right through our zeros. That was picking some random point in our computation of accepting this string. Right? So the configuration, every time you make a transition, you're going from one configuration of the machine to the other. So that configuration we would represent with X, X, Q1, 0, 0, Y, Y, 1, 1. So you take everything to the left of where your head is, put it there, then put what state you're currently in, then everything starting at your head to the right here. And we call that a configuration of the machine. Now, when this machine reads 1, 0 and moves to the right, the configuration it's going to be in is X, X, 0, Q1, 0, Y, Y, 1, 1. That's reading 1, 0 and moving to the right. Because we'd still be here.
Right, but wouldn't our state be Q0 at the beginning? Because if we're like starting on a
Yes,
0.
our start state would have been, if we went back to the very beginning, our start configuration would have been Q0, 0, 0, 0, 0, 1, 1, 1, 1. That was our start configuration.
I meant the first configuration that you wrote, the one that's
This
in the
one?
middle now, yeah. Shouldn't that be Q0 instead of Q1?
I assume that this was when we were right here, just after replacing. Oh, oops. Yeah, you're right. We need an extra X here and then Q1 there. Okay.
Okay, that makes more sense.
Yep. Good. Good catch. So that would be 0, Q1. Okay. Good. So that's what we call a configuration. So now let's read the actual definition and hopefully it makes sense. For a state Q and two strings UV, and they're strings of tape symbols, we write UQV for the configuration where Q is the current state we're in, UV is the tape contents, and the head location is the start of V. So configuration is U, all the symbols to the left of our head, Q, and then V, all the symbols starting at our head to the right, where the head location is the start of V. Make sense? There's our precise definition. So, example, let's say that we've got some random Turing machine. We know we're currently in state Q5 in our state control over here. And this is what our tape currently looks like. How would I write this configuration? My configuration would be 0, 1, X, all the symbols to the left of the head. Then the state that we're currently in, Q5. Then, starting with the head, all the symbols to the right, Y, 1, 0. That's the current configuration of the machine. Good? Awesome. All right. We say that configuration C1 yields C2, kind of like what we had here. This configuration yields this configuration. We went from this configuration to this configuration in one step. So we say that configuration C1 yields configuration C2 if the Turing machine can legally move, missing the word move from C1 to C2 in a single step. Pretty straightforward. So, as an example, suppose A, B, and C are tape symbols, and U and V are strings of tape symbols, and that Q sub I and Q sub J are two states. Then, we could say that some string of tape symbols followed by a tape symbol, QI, a tape symbol, some strings of tape symbols, yields UAC QJV. Notice what happened here. Our head moved to the right, so our head used to be right here. It replaced B with C, moving to the right, and our state changed from Q sub I to Q sub J. So this configuration yields this configuration if, on input, state Q sub I and our head pointed at B, if delta of that is equal to Q sub J C when we move to the right. Similarly, if we would have moved to the left, so if we would have moved our configuration to the left and replaced A with something, like C, so U, A, Q sub I, B, V yields U, Q sub J, C, B, V, if Q sub I and B is equal to Q sub J, C when we move to the left. So one of those was replacing B with C, moving to the left, and one of those was replacing B with C, moving to the right. No? I wrote this wrong. If we replace B with C and move to the left, then we look like this. U, Q sub I, or Q sub J now, since we changed our state, we'd still have our A there, and then it'd be C, V. We replace B with C and move our head to the left. Sorry. In both cases, we're replacing B with C. In one case, we move to the left. In another case, we move to the right. If we move to the right, here's what our configuration looks like. If we move to the left, there's what our configuration looks like. Okay. What is a start configuration? A start configuration is our start state followed by our input string. A Turing machine always starts out with the input, with the tape just being the input string. That's how the tape always starts. Right. The tape always starts with just the input string. So the start configuration is just the start state and the string we're trying to recognize. Make sense? All right. An accept configuration is a configuration, any configuration that has a Q accept in it. A reject configuration is any configuration that has a Q reject in it. A halting configuration is either an accepting configuration or a rejecting configuration. Both of those are called halting configurations. The machine stopped running. It came to an end. It halted. Okay. New definition. A Turing machine M accepts some input W, provided that there exists some sequence of configurations, C1, C2, C3, C4, all the way to Cn, such that C1 is the start configuration, Ci always yields, the current configuration always yields the next configuration for all I between 1 and n minus 1. Why n minus 1? When we plug in n minus 1, we're going to get C of n minus 1 yields C of n, which is the last configuration. So we have C of 1 yields C of 2, C of 2 yields C of 3, C of 3 yields C of 4, dot, 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 dot. C of n minus 1 yields C of n. And those were all our configurations. And then finally, it does if C of n is an accepting configuration. So if those three conditions are met, a Turing machine accepts the input W. So a Turing machine accepts the input W if there exists some sequence of configurations such that the first configuration is a start configuration. Every configuration legally follows. Every next configuration legally follows from the previous configuration. That's what this is saying. And the last configuration is an accepting configuration. If you can find some sequence of configurations that satisfies those three conditions, the string will be accepted by that Turing machine. Similarly, a Turing machine M will reject some input W if there exists some sequence of configurations such that the first one's a start configuration, each next configuration legally follows from the previous configuration, and C of n, the last configuration, is a rejecting configuration. That's the only time it rejects. Notice that a Turing machine does not have to accept and it does not have to reject. It could do something like an infinite loop. See, we didn't have that problem with like push-down automata because we keep reading the next input. So we didn't have that problem with finite state machines. We didn't have that problem with push-down automatas. Since we don't automatically stop a Turing machine just because we reach the end of our input, it's possible that Turing machines go on these loops that never end. Or he gave it some impossible process that's just going to run forever and never accept and never reject.
And we haven't been able to prove that we can't prove that we can ever solve that problem, for instance.
Yeah, we will prove that if I gave you a general Turing machine, you cannot in general determine if that Turing machine will halt on an input string. There's no way for you as a programmer to tell the difference between the Turing machine is just taking a really, really, really long time to solve this problem versus this Turing machine is never going to solve this problem. I mean, just because your computer takes 1,000 years to solve a problem doesn't necessarily mean it couldn't solve the problem. Maybe it needed 1,000 years and 1 second. And you decide after 1,000 years exactly, okay, it can't solve the problem. There's no way for us to, in general, determine the difference. Okay, and we'll prove that later with the halting problem. I think in this book we do the acceptance problem, but logically equivalent. Okay, we're right here. We call the collection of strings accepted by M the language of M, or the language recognized by M, written the language of M, just like we know and love from all the other machines. Right? Okay. Now, two definitions. It's crucial that you understand on a high level the difference between these two types of languages. Because a lot of the class from here on out is going to be a distinction between these two types of languages. So, first definition. A language is Turing recognizable. Mathematicians call it recursively enumerable. Computer scientists call it Turing recognizable. So, a language is Turing recognizable if some Turing machine recognizes it. What does that mean? If I can create a Turing machine that accepts every string that's in the language, then that language is Turing recognizable. Okay. Now the one that seems a bit more tricky. Now a language is decidable. Mathematicians say recursive. Computer scientists say decidable. A language is decidable if some Turing machine accepts every string in the language and rejects every string not in the language. So what did we mean by Turing recognizable? That means that there exists some Turing machine that's able to accept every string in the language. What does it mean for it to be decidable? That means there's a Turing machine that's able to accept every string in the language and reject every string not in the language. A decidable machine is much better than just a Turing recognizable one.
I remember like the pictures that you were showing us of like the undecidables and then decitables and stuff like that. So are undecitables like by definition Turing recognizable but not decidable?
There is a hierarchy beyond just these. So undecidable includes everything outside of decidable, and there's a whole hierarchy there.
Okay.
And so yes, now if we were to create that hierarchy, so we had whatever, here we had decidable. Here we would have Turing machine, Turing recognizable. And here you could have even higher structures that computer scientists don't really study, but mathematicians do. If you did a study of the complexity of sets, that's what this is from a mathematician's perspective. And there are other levels here.
Okay.
We call everything outside of this circle undecidable.
Oh, okay.
Okay. But yeah, we're not as interested in this class in those higher structures. We're just interested in what's decidable versus what's just recognizable.
Right.
Because if it's not even recognizable, if we can't even build a computer to recognize the language, computer scientists aren't that interested in.
Yeah.
Can you give an example between Turing recognizable and decidable?
Turing recognizable and Turing decidable? Yes, we will see lots of examples.
Great.
The acceptance problem will literally be that exact thing. I don't know, are you already comfortable with the halting problem?
Yeah.
Okay.
I went and researched it.
Wonderful. So a halting problem, will a string cause my program to halt? That is recognizable. If the string will cause a program to halt, you can always find that out. I just have to wait long enough. So the halting problem, the strings that will make my machine halt, that's recognizable. If you just gave me strings that would make my machine halt, I can recognize each of those because it will eventually halt. But if you gave me a string that won't eventually halt, there's no way for me to know that it won't eventually halt. Maybe it just need more time to run. So that's kind of some intuition for the difference between these two things.
So there's
And why computers can always are good at one thing, but the other one gives us a problem.
So something that never halts is recognizable by a Turing machine, but not decidable.
If something can be recognized by a Turing machine, then it will eventually halt. If you only give me things that will eventually cause my machine to halt, then I'll always be able to tell you that those things will cause my machine to halt. I just have to wait long enough.
Yeah.
And it will eventually halt. But if you give me something that won't halt, now I'm in trouble. Because I don't know that it won't halt. For all I know, it just needs more time to run. Anyways, yes, we'll see lots of examples and we'll prove that some are one way and not the other. Okay. But important that you understand the difference between those two languages. Those two classifications of language. So no, if a language is decidable, it's definitely Turing recognizable. Decidable means we know when it will accept and we know when it will reject. Turing recognizable means we only know when it will accept.
That makes more sense.
Okay. And we already mentioned that. Okay. Let's move to the next whiteboard. Okay. More examples of Turing machines and constructing now a decider. Before we also constructed a decider. Most times when you write these things, you're going to be writing deciders. Okay, so our job is to construct a decider for the language B equal to W hash W where W is some strings of zeros and ones. So it's going to be some string, hash, and then that same string again. Now this is one that we knew a push-down automata could not recognize. We proved with the pumping lemma that we couldn't, I think we just proved WW, but we could have also proved this one. W hash W. This is a language that a push-down automata could not recognize. But a Turing machine will be able to recognize it just fine. And so we'll show that. Okay. What is our idea going to be here? So our idea is we're going to start out with a string like this. What am I going to do? I'm going to mark a 1. I'm going to mark whatever symbol I see here with an X. That's going to be a 1 or a 0. If it's a 1, I'm going to mark it with an X. And then I'm going to look to the right until I get past my hash and look for a corresponding 1 and mark it off with an X. I'm going to go back to the beginning. I'm going to see a 0 there. I'm going to mark it off with an X. Go until I see a corresponding 0, mark it off with an X. Go back to the beginning. So I'm going to look like that, mark them both off with an X, mark them both off with an X again. Eventually I'm going to have something that looks like that. If I have something that looks like that when it's all said and done, we were good. If anywhere along the way we ran into a problem, we reject the string. So now, I'm going to rewrite out this string, a smaller version of it, so to try and help give you intuition for how this machine runs. So we'll do 1, 0, 1, hash, 1, 0, 1. Good? And our head starts out right here. Okay, so we start out here. Now notice I have 2 arrows coming off of here. One keeps track of the fact that I saw a 1, so I'm ultimately going to have to match with a 1. This one keeps track of the fact that I saw a 0, so I'm ultimately going to have to match with a 0. In our case, we start off by seeing a 1. So I'm going to see that 1, I'm going to replace it with an X and move to the right. Now, when I see that 0, all the zeros and ones, I may just want to keep moving to the right. Because now I don't care until I get to the hash symbol. So that's what this one's saying, just keep moving to the right until you see the hash symbol. So that gets me to the hash symbol. Then when we see the hash symbol, move to the right. Now, notice that we saw a 1 marked with an X. We're going to have the same thing here. We see a 1 marked with an X. See a 1 marked with an X. And this time move to the left. So now we are right here. We see the hash symbol. We move to the left, which now gets us right here. We see a 0 or a 1. We move to the left. Clear until we see an X. When we see an X, we move to the right, and we restart our process. So now my head's right here, and I'm back in the start state. And repeat. This time we see a 0, so we come down this path. 0, mark it with an X. Puts us here. Read through all our 0s and 1s till we get to the hash symbol, moving to the right, which gets us here. See the hash symbol move to the right, which gets us here. Every time we see an X, move to the right. X, move to the right. And X, move to the right. Forgot to put those in. Which gets us to here. And now we see our corresponding 0. Notice if instead we saw a corresponding 1, we would have rejected. Because then it wouldn't have matched what we had here. Since we see a 0, we're good. We can replace that with an X. And we move to the left, which gets us here. Move left through all our X's until we get to the hash symbol. Once we get to the hash symbol, move to left, which gets us here. Move to the left through all our numbers till we get to an X. Once we see an X, move to the right and go back to the start. And repeat. And then going through that all one more time, we will mark that with an X, we will mark that with an X, which will have left us right here. Then we would move left through all our X's, which would have gotten us here. Move left through our hash symbol, which would have gotten us here. We would have moved right when we saw an X, which would have put us back on our hash symbol. Now, if we see a hash symbol, move to the right, which puts us here. Move to the right through all our X's. which puts us here. And then if you see a blank symbol, that means we matched off all our terms and we're ready to accept. If we would have saw another 1 or 0 there that we didn't mark off, then we would have rejected. Make sense? Okay. Let's do one more of these. It's the last one of these I'm going to do, and then we're never going to actually draw out a Turing machine again. It's good to get to the point where you feel like if I were to describe to you exactly what we were doing here, you feel like you could have reproduced the machine yourself. And hopefully you kind of feel like you can do that. Maybe it'll be a little bit hard the first time, but maybe after doing a few of them, you'll be fine.
It seems like it's a lot easier to understand the other machines that we've been working with.
Really?
Yes. Because it's more like controllable. You have, you know when something's going to end. You're not trying all possibilities. There isn't all these abstract.
I guess with the PDAs, then, yeah, we were always using non-determinism. So, I guess, yeah, if you don't like that, since this is all deterministic, that's probably nicer. Okay, next, we're going to do a decider for 0, 2 to the n times. So, let's get comfortable with strings in this language. Is this a string in this language? If n is 0, 2 to the 0 is 1, so 0 one time is what that means. This we're doing actual math, and then we're saying that many zeros. Maybe it would have been better to do something like a lowercase a here. Shouldn't have done a number, sorry. That would have been a better choice. So we're going to do an a 2 to the n times. If n is 0, that means a once. So this would be in there. If n was 1, 2 to the power of 1 is 2, so a 2 times is in there. If n was 2, 2 to 2 is 4, so a 4 times is in there. If n was 3, then 2 to the 3 would be 8, so a 8 times. So it's these strings. So 3 a's would not be in the language. The number of a's essentially has to be 1 or a multiple of 2. Make sense?
Yeah.
Okay, what's our strategy going to be for this? So pick some string of, now we'll use 0 since that's what I have in my machine. So I'm not going to replace all those with a's. So here's our strategy. Let's do one that we know is in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. If I know that this string has a multiple of 2 zeros in there, I can keep crossing off half the zeros in every pass of the string. I keep looping over this string, crossing off every other zero, crossing off half the zeros. If I can keep doing that until I have only 1 0 left, then the string was a multiple of 2. So let me show you what I mean. So I'm going to come, there's a 0, cross off the next one, there's a 0, cross off the next one, cross, 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 cross off every other 0, and restart. Come back, 0, cross off the next one, 0, cross off the next one, 0, cross off the next one, 0, cross off the next one. Restart. We're dividing the number of zeros by 2 each time. So first we had 16 zeros, then we had 8 zeros, then we'll have 4, then we'll have 2, then we'll have 1. If this ends up being the case, then the number of zeros we had was a multiple of 2. So that's essentially what we're doing.
Can we try that with a string of 15 zeros? Because in my head we still end up with 1 0 left.
Sure, but so following through with this, so now we have a 0, we're going to cross off that, 0, we're going to cross off that, finally restart, 0, cross off that, and we're done. When we get down to 1, we know we're good. Now, Emma says try a different example. You okay with doing 7?
Yeah.
So let's do 7 zeros this time. So if we did 7 zeros, 1, 2, 3, 4, 5, 6, 7. 0, cross off the next one, 0, cross off the next one, 0, cross off the next one, 0. We don't have a next one to cross off, reject.
Oh, okay.
So we better always have a next one to cross off, otherwise there was a problem.
So it rejects it if it's odd for sure, but
What about
yeah,
6?
Okay, let's do 6. It will work the first time and then crash the second time.
Oh, yeah, okay.
So 6, 0, cross off the next one, 0, cross off the next one, 0, cross off the next one. Repeat. 0, cross off the next one, 0, we don't have one to cross off, reject.
So when you get an odd number, you know we did it wrong.
We keep dividing by 2 until we only have 1 left.
You always eventually get an odd number if you keep dividing any other time.
Right, if our number isn't a multiple of 2's, then eventually dividing it by 2 will leave us with an odd number.
That makes sense.
Okay, so that's high level, our thinking here. Now with my machine, notice that we always leave this 0 alone. And we always go back and restart with that 0, right? So my machine here, I'm going to mark this first 0, the one that we always have when it's all said and done, with the special symbol, dollar symbol. Dollar symbol means my first 0, that's going to be the only 0 I should have when it's all said and done. So don't get confused by the fact that we have that dollar symbol. Okay? Alright, so let's walk us through the machine. I was going to write configurations as we did this one.
Wait, just out of curiosity, okay, so you just switched out with a dollar sign, but if you're ever heading back one direction, how do you know when you got to the beginning of your tape?
So with the Turing machine, as a best practice, you want to have some symbol to keep track of the fact that you've gone to the far left as you're going to go. Technically speaking, a Turing machine, if you're in the leftmost head position and you try to move left, it just puts you back to the leftmost position.
Okay, so if I try to go left and there is no left, I stay where I am?
Then you stay where you are, and the head stays there.
Weird.
Right. So that's something that would be really ugly to try and capture in a diagram. And so always just set your diagrams left. That never actually happens. So no one ever actually tries to go left of the leftmost cell. They always write their programs left. That's not a thing.
Try putting in a dollar sign or something to check.
Or something, right. So that's why I'm going to mark my first 0 with a dot. So let's do this. We'll do 8 zeros here to mark it out. So 1, 2, 3, 4, 5, 6, 7, 8, and then we have just blank symbols from there on out, off to infinity. Okay, so in our first state, if we read a 0, so our head's right here. In our first state, if we read a 0, replace it with the dollar sign, move to the right. So now we're right here, we replace that first symbol with a dollar sign. Okay, so we had a 0, so now we're going to mark off this first 0. So over in this state, in Q2, we're going to take a 0, replace it with an X, and move to the right. Cross it off. So cross off this 0, replace it with an X, move to the right. So now we're here. Now if we see a 0, just move to the right, because this is one that we're not going to cross off. Now, when we see a 0, replace it with an X and move to the right. Now when we see a 0, just move to the right, because that's going to be a 0 that we don't cross off. Now when we see a 0, mark it off and move to the right. And so we'll get an X here, we'll do 0 there, and then we'll get an X here, and we will move to the right on that last one. 0, X, move to the right. So we'd be in state Q3 right now with the head there. Right?
Right.
Now, if we see an empty symbol, move to the left. So that moves the head to the left. Now, through all our 0s and all our X's, move to the left. Basically, we're going to go back and find that first 0. So now we're going to move left through all these symbols, until we get to the dollar sign. Once we read the dollar sign, we're going to move to the right. And notice that reading that dollar sign is equivalent to, okay, we've seen a 0, so now the next 0 we need to mark off. Remember, our dollar sign's a 0. So now we're here, we need to find a 0 to mark off. If we see an X, just move to the right. Oh, there's our 0. That's the 0 that we're going to mark off. So 0, replace it with an x, and move to the right. That puts us here. If you see an x, just move to the right again. Now that 0 is one that we're not going to mark off, which takes us down here. We just move to the right. We ignore the 0, move to the right, or ignore the x, move to the right, which gets us to the 0. The 0 we replace with an x, which gets us back up here. X we move to the right, which gets us here. X we move to the right, which gets us here. Empty symbol we move to the left, which gets us here. Then we move to the left through all our x's and o's, which gets us back to dollar symbol. Dollar symbol we move to the right, which gets us here. When we read the dollar symbol, that means we read a 0. So now the next 0 we need to mark off. All the x's move to the right, x move to the right, x move to the right. Now we have a 0. 0 we mark with an x. And now we're in this state. All the x's move to the right, da 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 da. Once we see a dollar symbol, we move to the left. Here, we move to the left through all our x's till we see a dollar symbol. Now we move to the right through all our x's, which will get us to here. And then, if we see an empty symbol, move to the right and accept. Good? Mm-hmm. And if it weren't a multiple of 2, then somewhere along the way over here, we would have gotten in this state and would have had another 0 to mark off. We would have instead seen the empty string here, or the empty symbol here, I mean. Did we ever use that x go to the right? I don't think we ever used that. No, we must have. Never mind. We must have. Anyways, okay. So there was that Turing machine. Let's do this Turing machine one more time, just showing out some of the configurations to make sure we're comfortable with configurations. So this time we'll do it on the input just 4 zeros. So our starting configuration is we're in state Q1 with 4 zeros. Now the first thing we're going to do is we're going to read that 0 and replace it with a $sign. And so that's going to get us in the configuration $sign. Now we're going to be in state Q2, and we're going to have 0, 0, 0 like that right here, right? And then we're going to replace that 0 with an x moving to the right. So that would give us $sign x. That would put us in Q3, 0, 0, right? And then we'd read a 0 going to the right, which would put us in Q4. So it would be $x0 Q4 0 would be the configuration. Then we'd read the 0, x move to the right. So that would be $x0 x. That would bring us back to Q3. And we'd be right here. Right? And then we can continue on. But that's showing the configurations that the machine would be in. And so a configuration is like a save file. It's capturing the current state of the machine. You could load it up that and start the process at that configuration. Good? Bit much to catch up on.
Trying to.
Yeah. And you missed out a lot. Probably didn't watch the previous lecture either, huh? So?
Last time I did that, it took me an entire morning. Because I was like pausing it, like trying to grasp it. When I'm here, you're just pushing me along and it makes it I get way more done.
Is that better or worse though? Because you can't pause.
Sure you can, just ask the question.
It's kind of like chugging, you know, not really savoring what you're doing.
All right. So now, that's the last Turing machine we'll actually write out from scratch. Really annoying and tedious to actually do that. And if we tried to solve more complex problems, actually drawing out these machines, it would be a nightmare. That's how we're not going to do that. So let's do another one with the way that people usually prove that these things are decidable. So example, we're going to create a decider for x to the n, y to the n, z to the n, where n is some natural number. So it recognizes strings of the form x, x, y, y, z, z as an example. If we put another x here, now it would not recognize that string. Good? Okay, so here's how you see a proof like this now from here on out. we give a description of the machine M, and we say the procedure that you would follow. And we assume that if you understand this procedure, if you had to, you could go back and build one of these machines to carry out the procedure. Okay, so let's do that. So M, on input W colon, first, what are we going to do? We're going to scan the input from left to right to ensure it is of the form X star, Y star, Z star, and return the head to, I guess it's fine how he's at. Return head to start, return the head to the start position, otherwise we reject. So what's the first thing we're doing? And this is a very common thing to do when you're just using words like this. It would have been tedious to create the Turing machine that recognizes this language. But we know that we could create the Turing machine that recognizes this language, right? Because this is just a finite state machine. X star, Y star, Z star, that's a regular expression. We can create a finite state machine that can do that. Obviously, we can create a Turing machine that can do that. It's just one that always just reads from the tape and never actually writes to it. But actually drawing that thing out would be super annoying, which is why we are trickier when we actually build these things. But with something like this, it's really easy to throw something like that right at the start. So what does that ensure us? That ensures us that we have all our X's, then all our Y's, then all our Z's. So already a string like this would have been rejected. If we would have had XX, YY, ZZ, X, this string is not the form X star, Y star, Z star. And so we would have already rejected any string that looked like that. You're going to notice that when we give our procedure, we're going to explicitly say when to reject and when to accept. So make sure it's of that form, otherwise we reject. If it is of that form, return our head back to our start. So now we're back to reading our first X. Okay. Upon reading input X, replace it with a capital A, and then scan to the right for a Y to replace with a B, and a Z to replace with a C. So now, I'm going to go, so my string might have been to the of the form XXX, YYY, ZZZ. What am I saying? I'm saying first replace this X with an A, scan to the right looking for your first Y, replace that with a B, and continue scanning to the right for your first Z, and replace that with a C. And hopefully you feel like if you had to, you could give me the states that did that. Okay? Once we did that, so scan to the right for a Y to replace with a B, and a Z to replace with a C. If an X or a Y couldn't be found, I think that's supposed to be a Y or Z, sorry. If a Y or a Z couldn't be found, reject. So if somewhere along the way I couldn't find a Y to mark with a B or a Z to mark with a C, reject. Couldn't be found, reject. Otherwise, return the head to the leftmost X. Otherwise, return your head back right there. Move left through all the nonsense till you see your first A. When you see the A, move it right back to your first X. Okay. Return the head to the leftmost X and repeat. Repeat this step. Upon reading input X, replace it with an A. Find the corresponding Y, replace it with a B. Find the corresponding Z, replace it with a C. If we couldn't have found the B or the Y or the Z, reject. Otherwise, go back here and repeat. We go back here, we replace A, we'd replace B, and we'd replace C. And potentially we could have still had another Z out here. Right? So that's finishing step 2. Now we can't return to the leftmost X. Once all X's are replaced with A's, scan input left to right to ensure it has no remaining Y's or Z's. So now we scan left to right, make sure it has no remaining Y's or Z's. If it does, reject, otherwise accept. So if we did have an X or Z out here, we'd reject. If we didn't, okay, we can accept. Make sense? And so that's how we actually write these things out, typically, rather than building massive diagrams.
You just describe it, basically?
You just describe the procedure step by step. Yep.
You almost build a programming language that says that exactly.
Right, this should almost feel, It's like a very verbose version of pseudocode almost.
Yes, like complicated.
Right, and that's exactly what you're after here. Explaining a procedure that feels like someone could easily follow. Hopefully someone could easily create a program, if they were a programmer, to do these exact steps. Okay, so that's that example. Any questions on that example? All right, move on to the next one. This time we're going to create a decider for x to the I, y to the j, z to the k, where I, j, and k are all at least 1, and k is equal to I times j. In other words now, we're going to build a procedure that recognizes multiplication. The number of z's is going to be the number of x's times the number of y's. K is equal to I times j. Number of z's is going to be the number of x's times the number of y's. Good? Alright. Let's draw a dummy string to the right here to help us think about it. And we'll just do 2 times 3. So for our x's, we'll do x, x, y, y, y. 1, 2, 3, 4, 5, 6. So there's one that should recognize. Okay. And our head obviously starts out here. So on input W, first ensure W is of the form x plus y plus z plus. Did we ever talk about the plus there? When you see x plus, that means x concatenated with x star. So it's as many x's as you want, but at least one x.
I was actually a little, when you showed that 0 with a 2 and then an n on the other problem, it was kind of like, it threw me off because I was thinking to the power of.
Yeah.
And it just seems like we could get consistent with the symbols, but.
Symbols are what they are. So, yeah, nothing we can do about it. But so when you see x plus y plus z plus, that is the regular expression x, x star, y, y star, z, z star. So, as many x's as you want, but at least one, followed by as many y's as you want, at least one, followed by as many z's as you want, at least one. This is a regular expression. Obviously, we could easily build a DFA which recognizes this thing, which means obviously we could easily build a Turing machine which recognizes this thing. Okay, so that's the first step. So ensure that W is of the form at least one x, followed by at least one y, followed by at least one z, and all your letters are in order. And then return the head to the start, otherwise reject if we got something that wasn't of that form. Good so far? Okay. Next, upon reading input x, so looking at this string now, so we know our string is of this form. Upon reading input x, replace it with an A. And scan to the right for the first y. So now our head is on our first y. Then for each y, replace it with a y with a line through it, while replacing the leftmost z with a c. If a corresponding z cannot be found, reject. So I'm going to replace this y with a y dash, come over to z and replace it with a c. Then come back over to this y, replace it with a y dash, and come over to the z and replace it with a c. Come over to this y, replace it with a y dash, come over to the z and replace it with a c. Once all the y's are y dashes, so we scan through that thing and there's no y's left, they're all y dashes, we're going to go through and we're going to replace all our y dashes back with y's. So we replace all our y dashes back with y's. Now we're going to scan to the left for the leftmost x, which will be that one. If an x is found, repeat step 2. We found an x, so we'll repeat step 2. What does step 2 say? It says replace x with an A. Then for each y, cross out the y while replacing a z with a c. Cross out that y, replace z with a c. Cross out that y, replace z with a c. Once all our y's are crossed out, Switching back to just regular y's. Replace all the y's with y, and then scan to the left for the leftmost x. If an x is not found, if an x is found, repeat 2. This time we don't find an x. Otherwise, scan to the right for any remaining z's. Scan to the right for any remaining z's. If a z were found, so if we did have another z there, we'd reject. If no z's are found, accept. The number of z's we had must have been the number of y's we had times the number of the number of x's we had. That's how that procedure works. Good? So, there's another example of a Turing machine. That finishes section 3.1. Next, we move on to variants of Turing machines. This is what we'll start with next time, but I'll briefly introduce the concept to you. What are we going to show with variants of Turing machines? We're going to show that all the variants of a Turing machine that you might come up with to try and make it more powerful don't actually make it more powerful. So you might think, what would happen if we allowed our Turing machine to stay instead of forcing it to always move to the right or the left? Would that somehow make it more powerful so it can move to the left, to the right, or it could stay? Turns out no, that doesn't make it any more powerful because we could simulate a Turing machine that had the ability to stay with our regular Turing machine. That's how we're going to show it's no more powerful. If I can use just a regular Turing machine to simulate this Turing machine, then this Turing machine must not be any more powerful because my regular Turing machine was able to simulate it.
Not to mention, if you have if it's if x stay, you just ask the question again, if x stay, it'd just be it doesn't really get you anywhere to stay in the same location as far as I can tell.
Well, if they decided I wanted to replace y with a b, but stay, that's the same thing as replacing y with a b moving to the right, and then replacing that letter with whatever it was and moving to the left. So you could simulate it with just a Turing machine. You just move to the right and the left, that's the same as staying. So since we can simulate this with just a regular Turing machine, it turns out it's not any more powerful. Now what if we made the tape infinite in both directions? Notice that a Turing machine just has an infinite tape in one direction. It doesn't go infinitely far to the left, it cuts off to the left. What if we made our Turing machine infinitely far in both directions? Does that make it more powerful? And it turns out no, and we'll show you next time how we could simulate a machine that had an infinite tape in both directions with a Turing machine that's just a regular Turing machine. Then the next one, what about if we gave our Turing machine multiple tapes? So instead of just having one tape, what if we would have given it k tapes, 10 tapes, 20, some number of k tapes? Would that make it more powerful? And we'll show no. We'll show how you could simulate a Turing machine that had multiple tapes with just a regular Turing machine. And then finally, the big bad one. What if we allowed our Turing machine to be non-deterministic? Does that, in fact, make it more powerful? It made it more powerful with push-down automata. A non-deterministic push-down automata was far more powerful than a deterministic push-down automata. Is a non-deterministic Turing machine more powerful than a deterministic Turing machine? And we'll show no, it's not, and how we could simulate a non-deterministic Turing machine with a deterministic one. So that's what we mean by variants of Turing machines. We'll show that all these things, they don't really add power, and we can't really figure out how to get a machine more powerful than a Turing machine. Meaning we can't figure out how to create a machine that can fundamentally solve different problems, recognize different languages, than what a Turing machine can recognize.
This might be throwing it out of ballpark as far as
Go ahead.
the scope, but is there anywhere in quantum computing that
Nope.
there's a connection?
So, any problem that a quantum computer can solve, your simplest, most dumbed-down computer from the 1960s could solve, given enough time and enough memory. With enough time and enough memory, the stupidest computer that's ever been built can solve all the exact same problems as a quantum computer. A quantum computer can solve them much faster, much more efficiently, but there's no new problem a quantum computer can solve that your most stupid computer can't solve.
Okay, cool.
As long as it's a Turing-complete computer. There's such things as computers that are just state machines, but as long as it's Turing-complete, yep, we don't know how to get anything more powerful. Any other questions? All right, then we'll continue with the variant of Turing machines next time.